Hello, Mrs. Suggs here with a video recording for Thursday, May 6th, and I'm going to be going over the last 6 organic reactions. In the video for Wednesday, we went over the first 5, and now I'll be giving you the equations and a little background on the next 6 organic reactions. Remember, you can always use this card when you're taking the test or the quiz, but not other resources. All right, so we are down to esterification, and esterification has a foldable that goes with it, and the foldable might be of use to you. The foldable which you have is where you have an organic reaction here. If you open up the foldable, you see that this is a particular organic acid. It has 1, 2, 3, 4 carbons on it and the carboxyl group at the end. That is butanoic acid. Over here, you have an alcohol with 3 carbons. That would be 1-propanol. When you take an acid and an alcohol and combine them together, you can break off part of each functional group. The big lesson here is that the functional groups are reactive. Notice that this part of the organic acid or this hydrocarbon chain part of the alcohol are not reactive. But when the 2 functional groups bump together, a water is removed and a bond is made between the organic acid and the alcohol. This makes for an ester, and you should be able to name this ester. And so to write an esterification reaction, you should be able to write either the structural formula or the name of any carboxylic acid and any alcohol, and it makes an ester you can both write and name, and importantly, water. Water is a product that's made from pulling out that HOH from between the 2 molecules and letting them stick together. I'd like you to read this here at the bottom, which is the description on your page. Esterification is a slow equilibrium reaction that can be driven in the reverse reaction. This is a commercial process, and it makes all kinds of flavorings and scents. This is an example of alcohols undergoing nucleophilic substitution. You'll hear more about that in just a minute. And going on to the next reaction, if you are following along with me, I am going through your class packet on organic reactions. Remember, you have 3 different class packets. The 3 class packets were first on hydrocarbons and functional groups, now on organic reactions, and there is yet a 3rd class packet in your next group of materials on instruments. So I'm now going to be looking at nucleophilic substitution. I want to emphasize to you that this is of halogenoalkanes. I would keep this in the name of this type of reaction in your mind. This is not just nucleophilic substitution. This is nucleophilic substitution of halogenoalkanes. Whenever you see a halogenoalkane as a reactant, I would assume that it's going to undergo nucleophilic substitution. I also clarify for you that you're going to see 3 types of substitution reactions as we look at organic reactions. On your purple card, number 2 is alkane substitution. That's where the reactant is going to be saturated, only single bonds and only hydrogen and carbon, an alkane substitution. This now is number 7, nucleophilic substitution of halogenoalkanes. Whenever you see any of the halogens, fluorine, chlorine, bromine, or iodine, attached to an organic compound, this is probably the type of reaction that's going to occur. And the next one will be electrophilic substitution that has to do with benzene only. All right, so if you look what's happening here, you have these color-coded chemicals. I'm saying that you're starting with something like CH3Cl. 1-chloromethane. And this reaction is going to pull off the chlorine. The chlorine is going to be removed from that molecule. It's going to be reacting with NaOH, but the NaOH is going to be split into its two ions. Interestingly, the NaOH will have the OH part come and take the place of the chlorine. Hence, it's called substitution. The chlorine comes off, the OH goes on, and that makes an alcohol. And notice what has to go home alone. The sodium ion and the chloride ion come together to form salt. Nucleophilic substitution is where the halogen is pulled off of the halogenoalkane and the OH from the sodium hydroxide is put on. A slightly more complicated compound here is chlorine on a propane molecule, so it's chloropropane. And it too can have the alcohol, the OH add from the NaOH to make an alcohol with the NaCl as your second product. Nucleophilic substitution. Please read carefully down here that this description is if a halogenoalkane is heated under reflux with an aqueous solution of sodium or potassium hydroxide, the halogen is replaced by the OH group and an alcohol is produced. You do need to know this also. This is the nucleophile. The NaOH is the nucleophile. And here are two other nucleophiles that can do this reaction. So instead of NaOH, the other reactant could be NH3, and you would get products, or it could be some compound like CH3CN, and you get your products. Both of those can be substituted on in the place of the halogen on the halogenoalkane, and you get two products. Electrophilic substitution is very specific, and you don't need to know a lot about it, but there are times where the benzene ring, remember we can draw, we can draw these six-sided figures and appreciate the fact that there are hydrogens on every one of these 6 carbons. This is where an electron-loving species, so it's called an electrophilic substitution, takes one of the participants of this benzene off, whatever it is, it comes off, and the electrophile goes on. So you see that the electrophile is added to the benzene ring, taking a hydrogen off. It's called electrophilic substitution. There's not a lot more you need to know about it, but do read the description, please. Amide formation. Amide formation parallels esterification. You also have a foldable for amide formation, and it looks very similar to the esterification foldable. Here, you have an organic acid. So here you have 4 carbons with an acid group, and you have an amine, 3 carbons with an NH2 attached to it. Those 2 molecules also have 2 functional groups that when they collide are very reactive. Water can be removed from the joining of those 2 molecules, and this is how you make an amide. An amine and an organic acid come together with the removal of water to form an amide. So, as seen on the board, you should be able to write out by name or structural formula any amine combining with any organic acid to make an amide. And don't forget that water is the second product. In both esterification and amide formation, you need to consider the formation of water. So you have esterification, nucleophilic substitution, electrophilic substitution, amide formation, and two more very simple reactions, saponification and fermentation. You might have known about these already. Saponification is the making of soap. Historically, in New York State, it's very interesting because back in colonial times, this was a big area, Albany, New York, a big area for making soaps. You might have heard of Colgate or Palmolive. Both those are big companies that worked in this industry in New York State. Notice that you need to know the reactants and the products. You take any fat, and that fat could be an oil, it could be lard, and you react it with a strong base, something like sodium hydroxide or potassium hydroxide, and it makes soap and glycerin. Soap and glycerin. If the strong base that you use is sodium hydroxide, you'll get a solid soap. If the strong base that you use is potassium hydroxide, you'll make a liquid soap. Please read the description here at the bottom and on the side of your sheet. The next reaction is fermentation. I know my family has been known to make both wine and beer at home, and I don't know if you have any family connections to this process, but it's where you take sugar from any fruit. You can make wine from grapes, but you can make wine from dandelions also. Any sugar from a fruit or a flower, and you just let that sugar react with the enzymes that are in yeast. I emphasize that you make two products. You make the alcohol that is the 2-carbon alcohol that is consumable and carbon dioxide. The carbon dioxide you allow to bubble out of the reaction. But if you don't let it bubble out, you will be making champagne, and that bottle will pop when you open it up because the carbon dioxide has created a pressure on the inside. So both those reactions are simple and just something you need to know. I do have the emphasis here that you need to be able to write with words the two products and the two reactants and the two products of both fermentation and saponification. Some of these you would be able to write the structural formula for, but not all of them. I remind you that this scheme of organic reactions has all of these reactions on it. You can look at them in more detail. Look at the reagents here. Look at the products here. Notice that for oxidation of alcohols, they include that second reagent that has to be the oxidizing agent, like potassium permanganate or potassium dichromate, as just an O. That O in parentheses means the oxidizing agent. On the back of this, I have the scheme. So you can carefully look to see what is made into what else. This sheet is in page 5 of your class packet, your organic reaction class packet. And it's just a good chance for you to tune your eyes. Tune your eyes. As you look at this, I want you to recognize these 11 types of organic reactions. You should also practice writing the names and or the structures of the products. I know this particular sheet doesn't say that you have to, but see, there's plenty of room for you to write these products by name or structural formula. So look at number 1. When I look at number 1, the first thing I see is a halogen on an alkane. So that's a halogenoalkane. Whenever you see a halogenoalkane, I would assume it's going to be nucleophilic substitution. There's the OH that goes on, so you'll end up with CH3, CH2OH, and the sodium bromide will be your second product. Here, for the number 2, you have only an alkane. Only an alkane. What reaction does an alkane do? Well, an alkane could combust, but you need oxygen to combust, and that's not your other reagent here. Remember, I said you can, although it's very difficult, to do an alkane substitution. I recommend that you do this sheet carefully. Check your answers in Schoology. Do it again. Check your answers. You can always practice again by printing up another worksheet. I show you the homework that you're going to be doing Thursday night. Once again, the answers are on Schoology, but you need to get used to this. Do the complete combustion reaction for ethanol, which is CH3, CH2OH, reacting with oxygen. Do you know the two products that that forms for complete combustion? Can you balance that chemical reaction? It's hard to balance in a structural formula written like this. So I would tend to put it together with all the C's together, C2, H6O. That's an easier way to balance this equation, C2H6O. I mentioned in the last video that you do need to balance all kinds of organic reactions burning, the combustion of many types of organic compounds. You should really practice that. The addition reaction of hydrobromic acid and 2-butene. You should be able to write those two products and give me, let's see, an addition reaction has only one product. One product. You should be able to write that in a structural formula or give me the name. I know this is a lot to practice, and the more you practice, the more comfortable you'll be with it. You and many other students before you can do this and do it well. On the back side of the homework for Thursday night, you've got to write the products of these organic reactions and give me the name. Remember, you can always use your purple card for remembering the names. I think you'll be able to do just fine as you work through this worksheet. What I've hoped to do in this video is give you an experience to see the last 6 types of organic reactions. Keep working on it, keep practicing. In Friday's video, I'm going to go over the class notes and the homework sheets with you to see how you're understanding those practice materials. I am also going to be posting videos by other IB chemistry teachers that might be specifically the kind of help you need to understand these reactions. I know this topic is a lot of memorization. In and of itself, that is not difficult. So I wish you all the best. Good luck, and thank you for watching this video. I'll see you tomorrow.